Welcome, everybody. I'm Karl. I'm the Executive Director of the Keeling Curve Foundation. Our mission is to continue Charles David Keeling's scientific legacy by advancing, promoting, and protecting long-term environmental observations. We have 4 lightning talks for you today, and then it'll be followed by a panel Q&A at the end. So please, for the virtual audience, put your questions in the chat, and I'll moderate the audience here. So our first speaker is Ralph Keeling, the founder of the Keeling Curve Foundation and professor of geochemistry at Scripps Institution of Oceanography, UCSD. Ralph researches long-term measurements of the major constituents in air, including CO2 and oxygen. Since 2005, Ralph has directed the Scripps CO2 program, which sustains the Keeling Curve. In other words, the record of carbon dioxide at Mānoa, begun by his father, Charles David Keeling. Ralph's current research focuses on refining estimates of sources and sinks of carbon dioxide using atmospheric measurements. Ralph received a Ph.D. in applied physics from Harvard University and a B.S. in physics, summa cum laude, from Yale. And now for that, I'll introduce Ralph.
Okay, so thank you all for coming. Thank you all for coming. Our purpose today is to talk about an important and often overlooked topic in the climate sphere, which involves making sustained long-term observations of the environment. And I'm talking here about measurements in the air. I'm talking about measurements on ice sheets and forests and in the oceans that really provide the ground truth that's the foundation for climate policy. And I think most people working in the climate sphere assume these kind of measurements are going on, someone's doing them, and they're just going to be there available for people to use and make decision making. But in fact, a lot of these measurement programs are quite vulnerable. They're sustained by the dedication of scientists without necessarily the same kind of dedication on the part of sponsors. Furthermore, as we move towards a world where we need even more action on climate, we're going to need more of these kinds of sustained observations. So we're in a position now where not only do we need to keep up with what we're doing already, we need to address the need for even more measurements going forward. So as Karl said, this event is hosted by the Keeling Curve Foundation. I'm speaking both as the president of the Keeling Curve Foundation and as a scientist engaged in making measurements of atmospheric carbon dioxide and other gases over time. I'm engaged in making long-term observations. So to illustrate the importance of long-term observations to policy, I want to turn to the case of chlorofluorocarbons, and particularly a compound called CFC11. So the programs that are the precursors of the modern NOAA and A-gauge programs that are making these measurements started in the late 1970s. And it was clear within a few years that there was an issue with these compounds building up, concerns about their impact on the ozone layer. And there was an observation of an ozone hole over Antarctica, which really spurred action, led to the Montreal Protocol in 1987. And within a few years, the curves bend over, and you can see that the reduction of emissions, essentially to zero in this case, was working. So observations informing policy, actually leading to action that's solving the problem. But the story gets interesting because sometime around 2017, my colleague Steve Monska at NOAA noticed that the curve wasn't bending the way you expected it to. It was starting to reverse and start to angle towards upwards again. And this was traced to illegal emissions from China. The Chinese government quickly cracked down, and within a few years, we were back again on the track we were supposed to. So it's a good illustration of how long-term observations, they identify the problem, they lead to a solution, the solution is verified, and then you can verify that you're staying on track or take corrective measures as necessary. So let's now look at the case of carbon dioxide. Measurements of carbon dioxide started by my father in 1958. Within a few years, he showed that CO2 was building up in the atmosphere. There was already lots of discussions about this. A White House report in 1964 led by Roger Revelle went to the President Johnson discussing how this was going to be a big issue for the future. Lots of other milestones here on the pathway towards climate policy. But of course, CO2 has just continued to rise and rise. And you might say, okay, well, this is a sad story that we haven't been able to bend this curve yet. But on the other hand, the CO2 record stands as a constant reminder of the call for action. And at some point, the curve will begin to bend. And at that point, it becomes a symbol of hope and can do. So I wanted to show this slide. So one thing to impress upon you is that if you're making measurements over the long term, it's really important to make measurements of high quality so they sustain, they stand the test of time. So this is a photograph of my father on the right from 1959, sweating the details. So that's him sweating, and all the details are over here. So I just wanted to point out that it's not just a matter of putting a sensor out in the field and getting data. Calibration is key, and calibration is a big part of the effort. I want to also mention work on atmospheric oxygen that I pioneered, and it's continuing in my group. We were able to show through precise measurements that the oxygen concentration of the atmosphere is decreasing over time. It's decreasing primarily because of fossil fuel burning. When you burn fossil fuel, you emit CO2. You also take oxygen out of the atmosphere. So this is showing oxygen decreasing on top with the parallel curve of carbon dioxide rising below. The decrease is tiny in relative terms and not an environmental concern, but it provides incredibly valuable diagnostic information on the controls of carbon dioxide. Every process or every major process that affects oxygen also affects carbon dioxide, like photosynthesis and respiration and fuel burning. Some additional processes, like the uptake of CO2 by the ocean or, say, dissolution of coral reefs, does not affect oxygen. So there's differences in their behavior, and by measuring them both together, you can get a handle on the global balance of the major sources and sinks of carbon dioxide. So you can diagnose not just that CO2 is building up, but where it's going. Finally, I want to turn to the example of sulfur hexafluoride. This is a gas that was measured as part of the same apparatus that is used to measure the CFCs, can also measure other gases like sulfur hexafluoride. So it kind of came along for free. Not quite, because you had to calibrate, but it was very clear within a few years that sulfur hexafluoride was building up. Sulfur hexafluoride is building up because it's used in high voltage systems like transformers, and where it leaks out and is accumulating in the atmosphere. Obviously, there's a problem here. This trajectory is just up and up and up. And moreover, we don't have good solutions for high voltage systems that don't depend on SF6. So we don't really have a pathway yet for bending the SF6 curve. And of course, we want to electrify our grid as part of the green revolution. So there's a collision of need and capability here. And I want to call attention to Eric Bayan, who's in the audience here, who's sponsoring or trying to launch an X Prize in SF6 to sort of put together new technologies that can actually help us on the right path. Oops, I didn't want to do that. Didn't want to give that away yet. All of these examples that I've covered so far involve measurements of atmospheric composition. But of course, we need long-term observations of other systems in the Earth system. And some of the other talks that will follow me will highlight that. And I should say my purpose today is not to give a science lecture or to point to but rather to point to critical vulnerabilities in the observations themselves. Now, the case of the CFCs is somewhat exceptional because the Montreal Protocol, which led to the bending of those curves, also mandates continuing measurements of these compounds. So the US would be in a treaty violation if it would be in a breach of treaty if it didn't continue these measurements. But what about carbon dioxide or oxygen, for example, that I measure? Well, that may shock you, but there is no such obligation to keep those measurements going. They continue because scientists continue to make them. Now, in the case of my program, how does this work out? So this is a graph that shows the Mauna Loa record of CO2, the so-called Keeling curve, but it also shows the way this record has been supported over time. So each one of those, image down below there is not the New York City skyline. It's the budgeted funding for this program over time. And a fair fraction of the funding has come from the National Science Foundation in different increments. I think there's something like 64 different grants and 12 different agencies that are reflected in the bundle of support that's evolved over time. You can see some agencies supporting for a while and then disappearing and then other kicking in. At the moment, the program is supported with a combination of money from the National Science Foundation and from Schmidt Sciences. And what this is a reflection of, as what I was saying before, it's a program that's sustained because of the dedication of scientists without a commensurate long-term commitment on the part of the sponsors. Now, don't get me wrong, we are incredibly grateful for the support we have gotten here reflected in these. These are all hero stories. These are people who are that made this money come to us. There's flexibility and broad-mindedness and maybe even some real courage to help this money come to us. So, and you might reasonably ask, if this program has continued like this so long, what's the issue? What's the issue going forward? Well, the real issue is vulnerability. I'm sorry, the real issue is the fragility and vulnerability. So how does a program like this navigate a transition in leadership? How does it navigate changes in the priorities of various agencies or funders over time? And what happens if I get hit by the proverbial bus, right? So this vulnerability is really society's vulnerability. And now let me say that when it comes to long-term observations like this, the community often engages in a kind of magical thinking. I have, of course, faced challenges, as my father did, in keeping these measurements going. And when I've encountered really rough patches, some of my peers will say, "Oh, Ralph, this is so important, they're just not going to let it happen." The problem with that statement is that there's no they. There's no they out there. Everyone assumes that sustaining measurements over time is someone else's responsibility, some magic other agent or force that's going to take care of this. But we're not just here trying to do research on fundamental research, and you could make a medical analogy at this point. We're not trying to cure a disease. We actually have a patient that needs caring for. That's our environment, that's our earth. And so we need to keep the monitoring going. So it's a special circumstances that really motivates this. So as the director of the program that measures CO2 and oxygen at the Scripps Institution of Oceanography, I'm partly here to make a plug for these programs. And I'm talking not just about measurements of Mauna Loa, but our programs also make measurements of carbon dioxide at other stations, of isotopes, and of oxygen, as I pointed out. And these programs are part of a larger community making measurements, of which a really prominent participant and leader is the National Oceanographic and Atmospheric Administration. But our measurements are an important part of that mix. We're sustaining the longest records. There's some of the best places to look for evidence of change. We're also measuring species like oxygen that NOAA is not measuring. And isn't it a bit weird that records as precious as these are still effectively being bootlegged on a shoestring budget with such an uncertain future? Now, these measurements basically provide a kind of ultimate bottom line, the canary in the coal mine. And we're not just providing science, we're also providing motivation for action and diagnostic as whether that action is working or not. So I'm making a plug just to try to get further support for these, thinking that there might be a role for philanthropy in this mix, or a larger role for philanthropy. Also, as the president of the Keeling Curve Foundation, I'm here to make a separate plug for our foundation. And our foundation's goal is to encourage, promote, and protect long-term measurements of the environment. The problems I face and the challenges I face are not unique. There's a large community that's struggling in the same kind of way. And my father had to endure a lot of challenges to keep these measurements going, not just keeping the funding going, but he also took a hit because he kept doing the same thing, and his peers thought he was being uncreative and therefore not really worthy of the status of his achievement compared to many of his peers. At the same time, he was an inspiration for people to continue. He was eventually recognized for his achievements, And so he was an inspiration for others to continue in these kinds of measurements. And so the goal of the foundation is in part to take up his dream of inspiring other people to continue in his footsteps, making measurements not just of CO2, but of other important elements of the climate system. And I guess another way to say it is the goal of the foundation is to put some flesh on that mythical they that's somehow out there to take care of them, to produce a presence that's actually watching this space and make sure we don't go off the rails. So I'll say a little bit more about these last 2 points in my closing remarks, but at this point, I want to hand the mic back to Karl to introduce the other speakers. So thank you.
Thank you. So our next speaker is Dave Karl, Professor of Oceanography and Director of the Daniel K. Inouye Center for Microbial Oceanography at the University of Hawaii at Mānoa. In 1988, Dave co-founded the Hawaii Ocean Time Series HOT program that has conducted sustained physical, biogeochemical, and microbial measurements at Station Aloha in the North Pacific, essentially the analog of the Keeling Curve in the ocean. And he's done this in the North Pacific subtropical gyre for 36 years and counting. Dave's research interests focus on marine microbial ecology and biogeochemistry, including the major element cycles, controls on phytoplankton and bacterial production, and the impacts of climate variability on microbial processes. Dave received his Ph.D. from Scripps in 1978, and his talk will be on the importance of long-term observations for monitoring the marine carbon cycle and marine carbon dioxide removal. So I just need to set up his talk.
Thank you so much, Karl, and aloha from Honolulu. Welcome to everybody, and thank you for your expressed interest in long-term observations of Earth systems. Ralph gave an incredibly inspirational introduction to the topic, and I hope to move on from there. So if we could go to the second slide, Karl. Thank you. Okay, this is just kind of an outline of my very short presentation today, the discussion points, if you will, what matters and why. I think I'd be singing to the choir if I told you that our planet was in a very fragile state. The human imprint is large and increasing. There is a critical role to play for ocean time series measurements. I call these the sentinels of the sea, and I will give you an example of the time series program that we've begun here in Hawaii in a few minutes. And then I'd like to end my presentation with a policy prospectus for the future on marine carbon dioxide removal. Next slide. In a very important benchmark paper in 1990 on time series measurements, John Magnuson, a fisheries biologist who used to work here in Hawaii and then moved to the University of Wisconsin-Madison, wrote a very important, thoughtful paper where he essentially made the case that without time series observations of the contemporary system, we are hidden in what he called the invisible present. We had no context of the past and no predictions for the future, as Ralph just showed very nicely for some of these atmospheric time series measurements that he reviewed. In essence, Magnuson's article, which was influential at the time, was a call to arms for ocean time series. Next slide, please. One back, please. So we gave this some thought and we set up a minimum requirements to start an ocean time series. This isn't something that had been very common, so we needed to think broadly about what it meant to begin a time series, because it's been said that the two things you never want to do is to begin a time series or to end a time series. Once you start it, it needs to be on a very firm foundation. So you need important scientific questions. That's first and foremost. You need an accessible representative study site. in our case, a site in the open ocean. You need logistical support, and for ocean time series, that includes a capable research vessel. And as Ralph pointed out, probably one of the most important but poorly understood requirements is sustained long-term funding. But you also need people. You need leaders as well as dedicated seagoing technicians, computer scientists, modelers, and administrative staff. And you also need hope, luck, patience, determination, and you need some time. Getting involved in time series measurements is not something with an immediate return for, let's say, early career scientists. It sometimes takes a decade or multiple decades to start seeing Earth system trends above the normal noise and environmental variability that occurs in most natural ecosystems. Next slide, please. So in 1988, we set up a ocean time series that we call the Hawaii Ocean Time Series. The acronym is HOT. We study Station Aloha, which is an acronym for a long-term oligotrophic habitat assessment. This observatory is located in the oligotrophic North Pacific subtropical gyre, roughly 100 kilometers due north of the island of Oahu, where I am today. Since 1988, on roughly monthly intervals, we have been visiting this site and making a series of comprehensive physical, chemical, and biogeochemical measurements, with all of our data publicly available at that URL at the bottom. Next slide, please. In thinking about the research that we do, I reflect back on this beautiful book by Donald Stokes called Pasteur's Quadrant. And in this book, Stokes makes the case for the continuum between basic and applied research. And he actually sets up a XY plot. On the y-axis, the quest for fundamental understanding, and on the x-axis, a consideration of use. And in these two extreme quadrants, he placed the research of Niels Bohr, the Nobel laureate in the atomic theory, as probably very high in fundamental understanding. And at the end of the other axis, he placed Thomas Edison, the inventor, the engineer, the business person, a person who seeded industry with novel ideas and inventions. And the book goes on to make the case that Louis Pasteur, the giant of science, the founder of microbiology, fermentation microbiology, vaccinations and immunization, pasteurization, that the work that Pasteur did is clearly in this identifiable high quadrant, the upper right-hand quadrant, with high use-based basic research. And we believe that long-term observations should also be placed into Pasteur's quadrant, because they not only create and disseminate new information about the Earth around us, but they provide data that improves models, informs society, and in our case, protects the sea. Next slide, please. So after many years, 36 years to be exact, of making roughly monthly measurements at Station Aloha, we have produced what we call the Aloha curve, which is the analog of the Keeling curve. Now I guess we should call it the Keeling's curve, because there are two Keelings, Dave and Ralph. So what's shown in red is the Keeling curve that is produced from observations, flask observations of CO2 at Mauna Loa Observatory, shown in this nice photograph on the right. And what's shown in blue are the observations at Station Aloha in the upper ocean. And you can see right away that the trend line is identical. In other words, there's as much CO2 coming into the ocean from the atmosphere, from humankind, as is accumulating in the atmosphere. And so the ocean is a sink for roughly 30% of the CO2 that we've produced since the Industrial Revolution. The other thing to point out is that the curve is less smooth than the atmospheric curve. And this is because the ocean is much more variable in terms of water mass structure and the biogeochemistry that goes on in the ocean that doesn't go on in the atmosphere. All of the biota, the phytoplankton, photosynthesis and respiration balance that Ralph mentioned, and so on and so forth. As CO2 accumulates in the upper ocean, the ocean becomes more acidic. And what's shown on the bottom is the ocean acidification from these direct observations. And this is the longest data record of ocean acidification of anywhere in the world ocean. And we published an earlier version of this plot, and it won the Best Paper of the Year award in PNAS because it was so novel and important. Next slide, please. So what are we going to do about this problem? How are we going to possibly bend this curve? Next slide, please. Thank you. We do have a path forward. What's shown here is the CO2 emissions per year on the y-axis versus time on the x-axis, with this dashed line at the top is business as usual if we did nothing, and a shaded gray area as if we stop fossil fuel use, which is highly unlikely, but if we did, we could get down to the near zero emissions mark, and maybe even go into negative emissions if we employed carbon dioxide removal and carbon dioxide sequestration technologies. So this is the path forward for the future. And next slide, please. In a recent report by the National Academies, published in December of 2021, there was an authoritative consensus report on how feasible it might be to remove carbon dioxide using marine ecosystems, either through nature-based solutions, shown on the left, or through engineered solutions, such as changing the alkalinity of the ocean on the right. Among the nature-based solutions, there are things like marine protected areas and reestablishment of coastal environments, ecosystem recovery. There are aquaculture systems of growing seaweeds and having the plants take up the CO2 and either using the plant material for biomass production or for other reasons, other purposes. And then there's this large option of ocean iron fertilization. And this is an effort that's being explored by a group called the EXOIS Group. It's a group of like-minded international scientists and policy makers exploring ocean iron solutions. And they have a beautiful website, and I encourage you to explore that. I think there will be a presentation by EXOIS this Friday at Climate Week. Next slide, please. And this is not something that we're just thinking about. In fact, our Congress, the House of Representatives in this case, just last week held a major hearing on navigating the blue frontier, evaluating the potential of marine carbon dioxide removal approaches. This was a hearing with testimony from experts, including Scott Doney, who for a number of years had been at the Office of Science and Technology Policy in the Executive Office of the White House. So this congressional hearing was set up to explore the benefits and risks of marine carbon dioxide removal, to inform the public on these risks and on the potential for developing this as a major technology, especially to identify the scientific gaps in understanding and the deficiencies that we currently have in the workings of the marine carbon cycle. Something as fundamental as that, we still are lacking a comprehensive understanding. And finally, they wanted to assess the technological readiness. Is the country ready? Is the world ready to move forward with large-scale open ocean deployments of marine carbon dioxide sequestration technologies? And I would leave you with this quote, "The future is today." This is not some futuristic thing that we're thinking about doing a century from now. People are actually thinking about doing this next week and next year. So I would leave you with this thought and this possible inspiration that we may have a path forward into the future. Thank you very much.
Okay, Julio is a retired federal scientist, formerly with the USGS. Julio's research focused on how climate variability and change drive regional drought, flood, and fire frequencies in the US, and how to define baselines of environmental change across various timescales. His early work on how tropical Pacific variability influences the annual occurrence of floods and wildfires in the American West challenged critical assumptions in flood and fire frequency. Concerned about season creep with climate change, he helped establish the U.S. National Phenology Network, or NPN, a large-scale network of repeated and integrated plant and animal phenological observations and the tools to analyze them at local to national scales. And his talk is titled, Tracking Climate Impacts on Seasonal Timing Through Long-Term Observations. Take it away, Julio.
Thank you, Caroline. Thank you for your attendance. So a brief roadmap of what I'm going to be talking about. First, I'm going to make some brief comments about the importance of seasonal timing to science and policy. Then I'm going to shift to an incredible example, and that is the global impact of the post-1980s regime shift in spring onset. And third, I'm going to introduce you to the National Phenology Network, which is a citizen science network at the continental scale that we started in the mid-2000s. And then some final thoughts about the importance of long-term observations in a non-stationary world. Next slide, please. So the cartoon on the left underscores the influence of seasonal timing on the Earth's biophysical processes at all scales. This includes energy fluxes, climate dynamics, atmospheric chemistry, biogeochemical cycles, soils and ecosystems, and all their interactions and their feedbacks. Now, a prime example is the expression of the annual cycle in the Keeling Curve. In the Northern Hemisphere, photosynthesis removes CO2 from the global atmosphere in summer, and aerobic respiration releases it in winter. Now, Ralph asked today's speakers, next slide, please. Ralph asked today's speakers to address the contributions of long-term observations to climate policy, and I just chose to feature one. So in the late 1990s, Camille Parmesan from the University of Texas and Gary Yohe, who's an environmental economist at Wesleyan University, met during the hard work of the third IPCC assessment. They were part of an important debate. Camille and three other biologists wanted to assign high confidence to evidence from LTO, from long-term observations, that 20th century climate change had already impacted ecosystems. And Gary and three other economists argued that the biologists were making too strong a claim, given the importance of habitat loss and other pressures on biota. So the third IPCC report chose to split the difference. So the debate between Camille and Gary led to an important collaboration. In a much-cited 2003 study, they undertook this meta-analysis of phenological observations and species movements worldwide. So for a group of species, they found that spring leaf-out and flowering advanced around 2 days per decade, and species distribution shifted northward around 6 kilometers per decade. They entitled their paper, A Globally Coherent Fingerprint of Climate Change in Natural Systems. Next slide, Caroline. So changes in seasonal timing quickly became a mainstay of both IPCC and our own national climate assessments. In 2019, I worked with others to formalize a national climate indicator system for seasonal timing and phenology shown on this slide. For those of you that hadn't heard the term before, phenology refers to the timing of events in the annual life cycle of plants and animals and how they're affected by climate variability and change. Some examples include flowering, leaf out, hibernation, emergence, mating, and migration. The fourth IPCC report in 2007 recognize, and this is a direct quote, that phenology is perhaps the simplest process by which to track ecological changes in response to climate change. Next slide, please. That seasonal timing has changed is pretty evident in the annual phasing of daily land surface temperatures in the Northern Hemisphere. Two important properties of the sine-like waves created by these seasonal cycles are their amplitude and phasing. Amplitude refers to the difference between the lowest temperature in winter and the highest one in summer. And phasing refers to the timing of the lowest and highest temperature. Here I'll talk only about shifts in annual phasing. Now in the Northern Hemisphere, phasing is strongly influenced by two main modes of atmospheric circulation that steer the advection of heat from the ocean to land. Phasing has actually shifted nearly 2 days earlier since 1950, with most of this change happening abruptly with earlier spring transitions after 1980. Now, this significant shift is not captured in climate model simulations, and the exact mechanisms for the changes are still being debated. This post-1980 shift left an abrupt and globally coherent fingerprint of earlier springs and everything that affects. Next slide, please. Let's take phenology, for example. A recent study relies on some of the longest phenological records in the world to illustrate the regime shift to earlier springs after the 1950s and especially after the 1980s. Included in this graph are dates for blooming in cherry trees in Japan and Switzerland, and 3 woody species in eastern China, budburst for horse chestnut in Switzerland, and oak leaf out in the UK. It's part of what these authors called the great acceleration of plant phenological shifts. Next slide. A more comprehensive study in 2016 analyzed time series from 44 spring-related environmental variables on land and sea from the Arctic to the Antarctic, calling attention to the global impact of the 1980 step change shown by the vertical line in red in each time series. And I apologize that I can't magnify those, but next slide, please. And we see this again in an algorithm of spring onset that we derived from phenological data and averaged for the coterminous US. And you can see the step change again after about the mid-1980s. Next slide, please. Now, I spent most of my career living in the American West, where I studied variations and trends in long-term records of climate, stream flow, snowpack, wildfires, and phenology. The post-1980s regime shift is evident in this composite of several relevant time series, including many of the things I just mentioned. The potential cascading effects of season creep and its legacy on the American landscape has always intrigued me. And this inspired me some 20 years ago to help launch a national citizen science network to help monitor and map plant and animal phenology in both time and space. Next slide, please. So the USA National Phenology Network, or NPN, is a large-scale network of standardized, routine, and integrated plant and animal phenological observations and the tools to analyze them at local to national scales. Since 2009, 30,000 observers have made 40 million observations for 2,000 species at 25,000 locations nationwide. The award-winning team that manages the NPN is based at the University of Arizona in Tucson, and they've been funded over the years by the university, the USGS, NSF, and other federal agencies. Our annual budget this year is $500,000, which is a bargain by any measure. Next slide. So the NPN team is responsible for a lot of things with a very small staff that include, sustained volunteer recruitment, retainment, training, and coordination, developing tools for entering, downloading, visualizing, and synthesizing observations, building derived data products and maps to support research, and decision-making. Next slide, please. So this is a brief example of our derived products and real-time mapping of spring onset timing anomalies every year. So the departures in spring onset, which is really particularly popular among the news media. This is the anomaly map for this year, day by day. 2024 was the warmest April in North America and one of the warmest Aprils in Europe and Asia. And you can see that this doesn't happen uniformly across the continent. You know, some places, in this case, the eastern half of the U.S. Have much earlier advancement of spring, whereas, you know, the West is highly variable, partly because of complex topographies. Next slide, please. So given the diverse array of large-scale and long-term ecological monitoring across our country, we're now poised to start integrating phenology and myriad aspects of U.S. ecosystems in space and time. You know, I don't know the cost of doing this. It's significant. And there's no guarantee that this will continue, but there's a lot of promise in these integrated networks. And the final slide goes back to some of the comments that have already been made by Ralph and Dave, and that is that long-term ecological efforts usually very frequently sputter or falter due to poor succession planning and dwindling or withdrawn institutional support. You know, for example, the National Phenology Network has struggled through several of these bottlenecks. And right now, we're actually exploring philanthropic and commercialization options to supplement federal grants. And the commercialization option is actually the most difficult one. And you know, this has only really been done in agriculture in the United States. So in a non-stationary world where climate and land use are changing in constant and directional ways, continuity of observations is critical. We must strive to support and sustain long-term observations, both local and large scale across the globe. And folks, we really got to bend the curve. There's so much at stake for our future. Thank you.
Okay, our last speaker is Steve Hamburg, EDF's Senior Vice President and Chief Scientist, where he oversees EDF's scientific efforts, including work on quantifying methane emissions from the natural gas supply chain and the use of remote sensing to measure greenhouse gas emissions. Steve has been actively involved in biogeochemistry, forest ecology, and climate change impacts research for over 35 years. Previously, he was an environmental science professor at the University of Kansas and Brown University, where he was the founding director of the Global Environmental Program at the Watson Institute for International Studies. Steve served as a lead author for the IPCC and was acknowledged as one of the contributing recipients of the 2007 Nobel Peace Prize. He received his Ph.D. from Yale in forest ecology and was a postdoc at Stanford. And his talk is long-term observations are essential for accelerating greenhouse gas emissions reductions.
Great. Thanks so much. Yeah, thanks so much. Yeah, okay. I want to build on the last three, but I don't drop something here. Three talks. We heard from Ralph about the atmosphere. We heard from Dave about the oceans. Julio talked about terrestrial ecosystems. And I want to, and Dave and Julio set me up perfectly in terms of, he ended with bending the curve. And before I talk about how long-term observations are absolutely essential to bending the curve, I do want to do a little bit on my own journey. And this picture sums up my career. Why? Because what you see is a red spruce tree with a red oak seedling growing next to it. One is the past and one is the future. When I started working on climate change impacts on forest, I'm a terrestrial biogeochemist, I thought this transition, which we're now observing with many bigger red oaks than this one, would be after I'm gone, after I've gone to wherever we all go. But in fact, already a couple decades ago, we started seeing in my long-term plots that I set up now 45 years ago, we started seeing these transitions, and we're seeing them across the region. And this is from New Hampshire. Whoops. Can I go backwards? Nope. How do I go backwards? Okay, great. There we go. Okay, thanks.
That doesn't work.
Yep. So I do want to talk about long-term research because we need to think a little broader than we traditionally do as scientists. So this is long-term research spanning 250 years. It's putting different types of data together. So on the left-hand side, you see spruce, and the size of the wedge is the importance of red spruce in the composition of the forest at colonial New Hampshire. This is from witness tree records from the surveyors who walked the entire state, and we have thousands and thousands of trees. When they're assembled, we could put the composition of the forest together. You fast forward to this phenomenal long-term record from the Forest Inventory and Analysis System, FIA, and we can take these same areas and quantify it and show that the number of spruce have dropped dramatically. Well, immediately you say, well, Steve, that's not climate change, that's land use. There's a literature, I'm happy to share it with you to show that in fact, yes, land use matters, but climate is actually driving this change. This is occurring because largely of climate change, acid rain's involved, land use involved. But the point is we have long-term records that we can use from ship records in the oceans where they've made observations. And we have to remember those are important because we can't go back in time, but there is a lot more in the historical record than sometimes we recognize. This work was done in the context of Hubbard Brook experimental forest, which is from the terrestrial side, one of the longest continuous records. So there's 60 years of very detailed climatological records and forest composition. And I've used that this is the experimental watersheds. I've used that to document much of what we saw in the previous slides. I won't talk about that, showing these trends and how you can see climate change across the board in this very long-term rich record. For spruce, you see this tremendous change in the distribution of temperatures in the winter, which is really putting red spruce in a position where it can't survive over the long term. Basically, you got a lot of temperatures right around freezing, and the trees just aren't physiologically adapted to deal with it. Now I want to transition to what I've been doing when I realized that my role maybe was better suited than looking at the impacts as I started my career and what I did in academia to how do we, as Julio set it up, bend the curve. So I want to talk about methane, where I put most of my work. It applies equally to CO2. When we do the global methane budget or the global CO2 budget, we've got the wonderful data we saw from Ralph and from others who built wonderful atmospheric observations grounded with empirical data. That's it. All the rest is modeled. We do not have empirical data of any large scale in this methane budget. There's pieces in it, but most of it is modeled. There is no sector, there is no long-term record for greenhouse gases empirically measured for any sector, full stop. That's a problem, because if any of you have been involved in measuring greenhouse gas emissions, what we discover is there are great uncertainties. The mean might be right, but you don't know actually where those emissions are coming from. On average, you can't mitigate on average. It's about specific places, specific situations, and we do not have high quality data. We are not collecting it, and we are not doing it long term. The bottom line, if we're going to bend the curve, we need to know what's being emitted. In this case, I'll talk about methane, where it's being emitted, how much is being emitted, and importantly, how is it changing over time? Those sound simple, but despite all of our focus on climate change, we have not focused concerted efforts to answer those questions. There's some people in the audience who've spent some time, I'm looking at one right now, to think about these things. But the bottom line is we need to bring long-term observations to the very problem itself, not just the impacts. And we've done it in the atmosphere through the Keeling curve and the incredible leadership. We need to bring this to the full spectrum. And I'll talk about some of the work that we're doing to do that. but I can't stress enough how understudied and underinvested. The work I'm going to talk about right now is all philanthropically funded. There's remarkably little government funding. So this is using a government-funded satellite, TRPOMI, put up by the European Space Agency in 2017. We took that, working with ESRON in the Netherlands, and tried to map with empirical data emissions of methane from the Permian Basin of New Mexico and Texas. That was sort of the first comprehensive effort. That was 4 years ago, and in this world, that was eons ago. But the bottom line behind this was, we do that, you can see we got a better set of glasses, but boy, the picture's pretty fuzzy. We can't get it to spatially resolved at high enough precision. We can't do this in many parts of the world because the precision of the instrument's not good enough. So we're starting to see a clearer picture. But what we really need is really high quality glasses so that we can create a really long-term record across these different geographies so that we really can answer those 4 questions, so we can maximize our investments in mitigation, which right now we're not doing. And to be honest, a lot of players in the field, industry, whatever, make a lot of claims about what they're doing that simply aren't accurate, and no one can demonstrate them to be otherwise. So we approached this problem by trying to, and now successfully, launch a satellite that would provide much higher precision greenhouse gas measurements. We focused primarily on methane, though we actually will be measuring CO2 as well. This was the launch last March on a ride share at SpaceX of MethaneSat. We are now generating data. This is actually from Methane Air, an aircraft version of it. We released on Monday our first concentration maps from MethaneSat, and next month we'll release our first flux data products. So the key here is most of these satellites produce concentration data. That's a great science product, but it's not something that's policy relevant. So we're producing actual, we've developed an automated inversion process, so all our data is put out as a flux data product. How much is being emitted where? This shows you across the Permian in 2 different basins, total emissions, as well as the spatial distribution of those emissions. It allows us to see large point sources. The key here is we need new kinds of data with high degrees of precision and with a commitment, as we've heard about, to long-term observations so we can really track what's going on and we can target our activities to meet the imperative that Julio ended with. We've got to bend the curve. And at this rate, we're going to bend it too slowly, in part because we don't have adequate data. And I don't hear anyone talking about the lack of data and the lack of long-term data on the mitigation side. We need it on the impact side and on the mitigation side if we're going to drive change. We at AEDF and with lots of partners are trying to change that. We need governments to weigh in. Philanthropic funding has been critical and important, but we're not going to do this just with philanthropic funding. This is the kind of comparative data we put out from our aircraft version of this sensor, of the spectrometer, flying across the United States in areas producing 70% of the oil and gas in the US. And what you see in the large bar is the total amount of methane emitted from those areas. You see in the purple at the base of it what the EPA estimated the emissions were from that same geography, and it's an average of 4 times higher than what they estimated. And then the emission rate and how it varies across these different basins. Well, this is a snapshot. This is comprehensive. This is the most comprehensive snapshot. Collins here has flown a lot of it in the past, but we did it all in a very short period of time across these whole basins with spatial distribution. We're going to do this across the globe. We will produce in the next 16 months the first quantitative estimate of emissions for an entire sector, or almost entire. We hopefully 90%. We've committed to 80%. Across the globe, empirically measured for an entire sector. I think it's amazing that up till now, we've never had that data set for any greenhouse gas, any sector. There's no way we can solve this problem without long-term, and the key is long-term. Snapshots, which some of them have been actively involved with, are great, but definitely not sufficient. It has to be long-term. It has to be regular so that we can really track what's going on. I believe that we are currently in a data revolution. If it survives, if we can really push it, get the correct funding, get the kind of, we're going to make a difference because we'll have radical transparency that we've never had before. And with that, we can really bend the curve in the way that we need to address the crisis that we're all in. The bottom line is that long-term, spatially resolved, directly measured greenhouse gas emission data is essential to effectively addressing the climate crisis. We have not confronted that up till now. Regrettably, NASA's not collecting this data. The European Space Agency is leaning in, but not as much as they need to. The Japanese Space Agency is, but nobody is producing across the board the data in a form that's directly policy relevant. They're not giving us fully resolved rates of emissions, and we need that if we're going to solve this problem. We need to think about the impacts that we talked about, the atmospheric changes, and the details of where those emissions are coming from. You put all that together, as we saw in the 4 talks, we do it over the long term, and then I think we actually have a possible future that may not be as dim as some of us fear it will be. But it will take that long-term work done in an effective way, in an integrated way, with sustainable funding. And so with that, thank you very much.
Thank you so much, Steve. We're going to take some questions from the audience first, and we're going to bring the 2 panelists up here, and then Dan is going to moderate the questions, any questions from the virtual audience.
Hi, I'm Sonia from the Data Foundation. So I think about this problem of science to operations a lot, in that science is now becoming a public good to answer climate decision-making questions, but that's not where we kind of are at the state of the world. And so in the US domestically, this is especially a problem with government funding, with the Congress we're in, and it's likely not going to get better. And like you said, we can't rely on philanthropic funding for this, and academia is limited in what they can do, and pushing forward, you know, science to answer science questions, science on the 2 to 4 time period, to PI driven to answer, you know, push the boundaries of the questions that scientists ask. And so what are your thoughts when we have this limited, you know, locked Congress that probably won't be a good partner in doing the things that we want them to do? And then knowing that, like, there is philanthropic support, but that's really to get things off the ground, get things moving, and to demonstrate, like, what is the untapped resource that you see that we could rely on, or that's currently being underutilized?
You want to go for it?
I guess a couple points. I think there ought to be a role for philanthropic curation, in the sense of, you know, a lot of philanthropy is trying to spur new technologies, new things going. But, you know, there's an old school of philanthropy where you maintain a museum, you're curating something that's of long-term value for society. And I really think it won't be big enough to address the full need, but it does seem to me that there ought to be a recognition that there is a role for philanthropy in that sense. And a very brief comment on the science to operations question. You know, most of the long-term observations that matter and are of quality are being done by scientists, and I'm not sure it makes sense to move those kind of operations outside of science. It's rather more important to recognize that those are part of a scientific enterprise, and they should stay there. And the issue isn't so much whether it's operational as whether there's a long-term commitment on the part of the sponsor. So an enterprise that has stable long-term funding and is engaging scientists who are not just making the measurements, but actually thinking about how to use them and are invested in their quality is the best way to square this.
I'm going to take a slightly different tact. I think, and certainly I've done this in my career, I moved from doing basic research, which I totally support. I did it for most of my career, but we need to make an investment in really good research, basic research, but that is part of a data to action pipeline. And that doesn't mean the scientists are doing all of that, but we can see the path from the data to action. Some of it's going to be slow, some of it's going to be fast, but we need to fund that. And I will be open, because I've said this in public. I said it in a National Academy meeting, a public meeting, is right. NASA should be investing in this kind of work. an NGO should not have to put up a satellite with much higher precision than anything NASA's put up to measure greenhouse gases. I'm sorry, something's wrong with that model. And that's what's happened. We have greater precision than NASA does in the satellites. They're slow. They don't currently make the measurements we need right now. And as I said openly in that committee hearing in the mid-decadal review, I was at the time at the COP in Dubai, and the problem was NASA was irrelevant to the conversation that was going on there. And that doesn't mean that, and Phil's going to push back on me. Okay, good. Okay. But I think what we need, philanthropy is critical, but not sufficient. So I'm not saying we shouldn't ask philanthropy to weigh in. They can help push the edge. What we need to do, and I'm seeing this in other places now, leaning in, and whether it's remote sensing, because we have to bring remote sensing in, because I'm a ground-based guy, but you just can't get to enough places to make these measurements. We just can't do it. It's not physically possible. There's other stuff that we heard about we need to do. So we really have to think about how do we bring these multiple sensing systems together to create a much more complete picture over the long term with consistency. And we are getting receptivity in other countries to doing that. And we need to bring that effort together, and there are multiple efforts to do it. Phil might talk about one that he's involved with, but we have to think about how that happens and the urgency. And I am seeing, I won't get into specifics, but I'm seeing some of that happening in other countries, less so in the US, where there's pressure because there's agencies and others who see the need for this data, and they lean into those who could produce it and say, hey, you got to produce more of it. And NOAA's certainly trying to do that. Colin's here, I won't put him on the spot, but they're making measurements that are more relevant. We got to accelerate that and do that in a much more deliberate way. And I'm not sure that the amount of money is going to need to be that big. It's about where do we put our emphasis, and is it data to action pipelines? So again, you're still doing good science, you're doing basic science, or is it doing science for its own sake? I'm all for science for its own sake, but that's not sufficient anymore. We can't just do that. We can't afford it because we're going to be fiddling while Rome burns.
I thought let's just ask Dave and Julio if they can respond to that question. And if you need the question repeated, let me know.
Well, this is Dave Karl. Thank you for that question, and thanks for this discussion. I don't have much to add other than the government, the structure of the government is not a long-term structure, so it kind of works against with a 2-year election cycle or 4-year election cycle, 6-year election cycle, depending on what leadership group you're in. They're not thinking decades into the future with policies. So I think, there needs to be, we need to rethink who's in charge and who's actually coming up with novel climate policy, and not so much who's implementing it, but who's actually directing it, who's developing the policy. Julio.
Yeah, having worked for a federal agency my whole career for about 40 years, I've come to understand the fact that our budgets in the federal government are flatlined. And the problem with flatline budgets is that it's almost impossible, unless you do it with end-of-year money, almost impossible to invest in long-term observation records and monitoring, because normally what happens is, I think Ralph referred to heroes that start these long-term observation efforts. And I think what we sometimes forget is that when those heroes retire or they die, the lack of a successional plan and the lack of temporary funding to make sure that they pass through the bottleneck is critical. And I don't think that necessarily comes from government. There has to be a different source of funding to do that.
Yeah, I actually want to strongly agree with what Steve was saying, but the details are really what we need to focus on. And the problem is that NASA, is not the right place for this activity. In fact, what's the right place is probably the Treasury Department, right? I mean, what we really need to be able to do is you said a key thing, Steve, which is that the focus has been on climate information services for impacts and adaptation. And there was a chance this past couple of years when there was an effort, Sonia was involved in it, OMB and OSTP and other parts of the Executive Office of the President and agencies got together to do what we thought was going to be the first time really going from carbon cycle climate research observations to an operational capacity to really deliver these kinds of critical, very valuable information to generate climate action and to target where the opportunities are at the right granularity and the right, surveillance, frequency and all that. And so it seemed like we were heading there, and they came out with this strategy, and the strategy had a lot of reasonable stuff in it. But it's a structural problem in the US government right now. It's like NOAA in some ways is the right place and is not the right place. NASA, there needs to be something created, first of all, which is an understanding that if we're going to transition from a high carbon to a low carbon economy, this kind of information that we're talking about here, these long-term observations with the right granularity and specificity and all those things, it's valuable stuff. I mean, we can't transition our economy, and it's part of that whole machinery. The IRA had all this money. The IRA, the Inflation Reduction Act had, just for example, $1.55 billion to EPA for the methane emission reduction program. You know what that money went to? None of it went to the kinds of things that we're talking about here. Yeah, it's a fart in a windstorm, though. It's not what we need, right? I mean, we really need to scale this up. And by the way, whoever else said about the government, I think the government is a critical piece, and the structural problems need to be solved to really create the understanding and the impetus of the value proposition that's associated here. But also there needs to be a public-private partnership. I think that it's going to have to scale up. It's going to have to be something where it's going to become industrialized in a way. It has to, we need to make it into a business proposition somehow.
So I largely agree with Phil. The one thing that I may disagree with him in is, how do we get there? We need radical transparency. All this data needs to be public, and we need to understand it. And developing a business model where you can do it in the private sector to generate it has been extremely hard. I've looked at numerous models. I know of numerous cases, and I do not know a good case for generating greenhouse gas data with radical transparency. So we can follow it and understand it. And all of us, whether we're in civil society or in the industry, everybody, I'm not talking about anyone, that's the challenge. So no, you have to do the science and you have to make sure. So I think we need to think about this model different. Philanthropy has a role, but I mean, it'd be great if it could be all done with philanthropy. I'm not seeing that level of commitment, because it's got to be sustained over the long term. Philanthropy just generally doesn't fund large things like that and just say, we're going to keep doing this for the indefinite future. They're looking for that to have a sustainable income to support it, and they move on to something else.
I grew up at NASA. I'm a NASA fan, but NASA is a research agency, and they're a self-proclaimed research agency. They don't want this job.
I understand they don't want it. We need them to help lean in on it.
Yeah, Ralph, you said earlier when you were speaking that on this question of funding, I think the importance of all this is clear, that, the comment of they won't let it happen, like, and who's the they, right?
Yeah.
On the other side of that, if someone had it just helped me understand, if someone had the check tomorrow, who do they write it to? Like, who's the they on who does it? right? Is it a whole bunch of people all over the place that are part of a disparate network, or is there like someone that they could write the check to who will, do the monitoring? And I guess
Well, okay, if it's if it's a check to my own research, I would know where to write the check. And if it's a check in the broader sense, I think that, we need a body that knows how to handle that. And it's my hope that the Keeling Curve Foundation can put together, a program and a structure and a responsible means of doing that. There'll be a lot of difficult questions involved in how to prioritize, how to find the funders and how to direct it to specific projects. And that's needs a lot of conversations between different parties that hasn't happened yet.
But so in terms of understanding that, is it right now, because I know, just take the CO2, there's different monitoring stations around the world. Are each one of those sort of off trying to raise money on their own to do?
No, it isn't.
How does it?
Yeah, it isn't. The efforts are not organized like that. I mean, you have individual labs like mine or the NOAA lab that Calm is here part of, that run a flask network. So there's flasks that go out and they're collected at various stations and then they come back. And then there's people who operate the stations that could be NOAA or some other international partner. So all the measurements are done in one central place, and the air is traveling back and forth. And then some of those programs also run remote stations. Like NOAA has like 4 or 5 observatories, Barrow, Alaska, Samoa. I could rattle off a few others, but where they actually have in situ instrumentation doing measurements over time. And there's another program, A-Gauge, which is some of the data I showed was from their program, and they run stations around the world. But it's a single program with collaborative across institutions that is maintaining these stations. So it's not like every individual site. There's not one investigator per site. It's one investigator per groups of investigators. Yeah.
And the trouble is, there are multiple models. So this model of creating like the foundation that Ralph's started. So for 30 something years, Hubbard Brook Experimental Forest has had the Hubbard Brook Research Foundation to do exactly that. And that's something that Gene Likens and Herb Borman set up, recognize the value of the long-term record and ensuring that there was a backstop, that the transitions that Julio talked about, that there's a mechanism. So there are some with these foundations, but it's a systemic problem, to Ralph's point, that we need to figure out how do we deal with this in a broader way. And we haven't. We do have some locations that have done it. You see the example of Rothamsted, which is probably the longest in outside London, and that worked. It went through some really rough times, but there were enforcement because of the nature of the will that set it up. So we have some successes and we have a whole bunch of failures, right? Where some great record was started and it's gone now because, and again, that's to Julio's point, but we can't, these are one-offs. And you have these mechanisms with government, but governments also de-invest. So the issue in Rothamsted is the government was funding some of that and wanted to de-invest. The terms in which they'd gotten the context in Rothamsted said you may not. And that was enforced. And that preserves some of the classicals and some of the, well, probably at this point, the longest continuous experiments in the world. We're approaching 200 years now. So, but we got to figure out something more systemic if it's going to work. There's our individual solution sets.
Yeah. Have we got time? Or maybe one more.
Is there one more question? Please go ahead.
I just have a question for Steve about your about what you were presenting on. I'm curious, if I understood correctly, the measurement that you were doing for the methane was unique in that it was like more location-based censoring. And so I guess I'm curious why you targeted methane to start, and also how that's going to be scalable like across different sectors and for CO2.
Sure. So we picked methane. We've been working on methane, and there are folks in the room here who've also been working on methane, because as a short-lived climate pollutant, a potent short-lived climate pollutant, if you can reduce the emissions, you can slow the rate of warming over the next couple of decades. So the way I like to describe it is we actually have 2 climate problems. We got to solve both of them. One is the near-term rate of warming. We got to slow it down. And the dominant is methane. CO2 contributes, but the dominant lever is methane. And quick action can happen. And then we have the longer term CO2 with N2O, where it's going to affect the total. We got to solve that too. It's not one or the other, it's both. But we had historically ignored methane because of the way some analytics, we used GWP 100 and it discounted it, and we sort of lost track of it. So we've leaned in on methane because it was understudied. And the advantage is because the differential, the delta, the delta changes in concentration in methane are a little easier to detect, so we can better map it. And so we've been able to take a sort of leap forward in our ability to do this. So we focused when we built the satellite was that we're going to do one thing is the best possible way. That's looking at methane emissions from oil and gas on a global basis. But that's not the only thing we do, but that we made the whole mission about that. We are partnering with the New Zealand Space Agency, and they've set up a whole team. We will be measuring agricultural emissions of methane as well. It's not as mature the science, but we'll be doing that as well. They're taking the lead on that. And so that's why we're doing methane. CO2, we just don't have enough downlink capacity. So we're testing our sensor, which has a lot of precision, to look at how useful will the CO2 data be. So we're testing hypothesis. I have some funding in place to do that, so that hopefully that can inform other satellites and other measurements, so we can say, oh, this data was really useful, or, not as much, because CO2 is quite different than methane because of these gradients and things. So that's sort of why we did it.
Thank you for the questions. We're going to just have Ralph do closing remarks, and then thank you for coming today. So let's see here.
So, it's been an incredible privilege to have been able to spend my life and my career working on something involving long-term measurements, and it's been a discovery process. It's been an exciting process, and I feel really grateful for the opportunity. I was, of course, inspired by my father, but there was more to do, and it was really an exciting voyage. At the same time, it's really troubling to me how vulnerable this whole thing is. I'm close to the end of my career. What happens in the succession path? And it would be a shame if it just came to an end. This was just my own personal journey of indulgence, and it ends at this point. And I really don't want to see that happen. So I'm here in part to make a plug for some kind of philanthropic support for the measurements we do. And in a way, how easy it would be just to ramp this up and put it on a different footing, and you'd get measurements that are really at the core of the conversation of climate. They have incredible scientific value because of their longevity, and they have incredible symbolic value for where we are and informing and motivating. So I'm partly here to make that plug. I'm also here to make a plug for the foundation. I recognize that the problems that I face are not unique. There are dozens or more of people making long-term observations who are facing the same thing, maybe with less visibility than I have. But the data is also super precious. And so it's in that context that I've launched the Keeling Curve Foundation with amazing support from people. And I thank everyone for coming here. I should maybe take a minute and say some thank yous while I think of it. But, we're really grateful for this venue, I should say. This venue was made available through the Schmidt Sciences and the leadership there, Stu Feldman and Balaji, and Dan Lee here. We're really great. Dan Lee particularly sort of helped shepherd us through this event. So we're really, really grateful for that. So yeah, back to the plug for the foundation. So what does the foundation want to do, and what's our goal? So first of all, we have a very distinguished science advisory council. Two of the speakers, Julio and Dave, are actually on our Science Advisory Council, and there are others there, and they're helping us shape our vision. But one of the things that we just want to do, it's critical and should be easy, is to communicate the significance of long-term observations to the public and private funders of science, because it's the first thing to do to get funding and to get support for is to make people aware of it. And a lot of people simply aren't aware of how important and how vulnerable these kinds of observations are. The other thing is to strengthen the community that's making long-term observations. So we feel like a whole. We're aware of opportunities and challenges across our community. maybe having a conference or training to support younger scientists so that they'll be inspired to make these kind of measurements and don't just view it as some career that the second-rate career. And then finally, to play some role in collaborating to protect long-term data sets with shepherding philanthropy in some way, in a responsible way in this space, setting priorities, and that's going to need more conversation, but it's a really important topic to keep talking about. So finally, in terms of tangibles, well, the one thing that's really shovel-ready and that we want to roll out, if possible, in the next year is an award, a Keeling Award in long-term observations. And this award would go to an individual or an organization who, like my father, played a transformative role in changing how we look at the world through long-term observations. We have a distinguished panel, independent of the Science Advisory Council, to go through a awarding process and a nomination process, and the committee will be run by a close friend of mine and a dear colleague, Jeremy Jackson, who's got a very broad perspective on these issues. And it'll honor achievers and young scientists who've made these kind of contributions. So the prize would include an unrestricted gift of $20,000 to honor the achievements, but it's mainly there to just put the spotlight on the importance of these measurements. And of course, this could be a struggling effort, and the recognition could also serve the role of helping anchor support for the measurements. So in closing, I hope you can join me in supporting our cause for the foundation. And I thank you for your time and your presence. And together, I hope we have an opportunity to really make a difference in this space. So again, thank you all for coming.